Okay, hello everyone. Hopefully you can all hear me okay. Do shout in the chat if you cannot. So as mentioned, my name is Jason Mays. I'm a creative engineer at Google. And today I'm going to be talking to you about machine learning. So some of you may have seen this before, but the audio quality is a little bit bad. So hopefully you can hear me perfectly this time. To begin this presentation, I just want to start by asking you a question. On the screen right now, you can see an animation of me holding a pen. A quick kind of show of hands or just type in the chat if you think this is machine learning. And bear in mind, I might be tricking you. It might be, it might not be. So don't assume anything. Just type in the chat if you think what you see is some form of machine learning. I'll give you a few seconds to do that. Okay, we've got some yeses and nos coming in. Good stuff. I think so. Yes, yes, yes. Okay, so the answer to this question is no, this is not machine learning. This is in fact plain old computer science, computer vision, and all I'm doing here is looking for the colors in the image and then putting bounding boxes around regions that are large enough to be the item I'm trying to find. Now, the reason I start my presentation like this is that machine learning and AI, all these buzzwords are very popular right now, but it's important to note that plain old computer science can still work in many cases, and it's often a lot simpler and easier to implement. So without further ado, let's bear that in mind as we go through the presentation. All right. So I mentioned I was a creative engineer at Google. What on earth is that exactly? Essentially, my role is to work with Google's top 50 customers around the world. And when they're launching a new product or service, I have to come up with a new idea that's never been done before to tell their story in a creative way using these latest technologies. Now, for example, you can see on the slide here, someone recommends making a hoverboard, and then the output is a hoverboard that works in a very constrained environment. Now, this is not an actual project I made, but it's a good illustration of the types of problems we deal with on a daily basis, where someone has a crazy creative idea, and then my job is to rein it in and actually make something that works in the real world so it can get attention. Okay. So let's go back 10 years. Now, I'm sure many of you may remember when there was a big shift to a mobile-first world. Everyone had desktop websites, and it never worked on mobile. And then there was a big industry shift to making it work on mobile phones. Otherwise, you'd lose business. Well, the same thing is actually going to happen with AI. We're going to move to an AI-first approach. So every industry will, in some way, be affected by AI in the not-too-distant future. Now, another way to think about this is this blog by Wait But Why. It's a very long blog, but I've taken some of the high-level concepts from here and tried to condense it down to this slide. Now, the author presents us with this image of intelligence versus time. And as you can see here, we've got ant, bird, chimp kind of equally spaced, and then regular human is a kind of a big jump from chimp, and then Einstein is another big jump from the human. Now, if we believe this to be true, we'd actually be wrong because AI is actually doing an exponential curve rather than a linear one. And the kind of difference in intelligence between these animals and humans is actually more equally spaced. And Einstein is only a tiny bit more intelligent than a regular human. And now another way to look at this is human progress over time. And here the author basically proposes that we're standing at the very beginning of this big uptick in progress. I believe by progress, he meant things like technological progress, innovation, that kind of stuff. And if this graph is to be believed, essentially what he's saying here is that in the next few decades, we may make more progress than we ever have done in the entire history of human existence, which is a pretty exciting time to be alive. Okay, so what is AI, machine learning, and deep learning? Once again, I'm turning to the chat. Please say yes or no if you've heard at least one of these phrases. Let's see your answers. I'm sure many of you have heard this in some shape or form. Okay, yeah, lots of yeses come in. Wonderful. Now, keep saying yes if you can tell me the difference between these terms. Or say no if you don't know the difference. Mostly, nope, no. Okay, we've got a mixture of results coming in now. Okay, cool. So you're in the right talk. If you do know all this already, then the first half might be a recap for you, and then it will get more interesting in the second half of the presentation for you. But let's get everyone to the same point. So let's start with AI, artificial intelligence. Essentially, this is the science of making things smart, or more formally, human intelligence exhibited by machines. Now, this term is a very broad term. And actually, right now, we're in a position where we develop systems which are in the realm of narrow AI. Now, narrow AI simply just means that we're creating systems that are as good or better than a human expert could be in one or two niche areas. For example, object recognition. And one great example of this is in the medical industry, where doctors are trying to scan for brain tumors. And in the past, you'd get back this very grainy image of a brain scan, and sometimes they'd miss the telltale signs of a brain tumor in that scan. Now, using AI, the AI can kind of point out regions in that image that may be more likely to have the tumor in, so the doctor can actually see it and recognize it without mislooking it. So that's one good example, but there's many other forms of where we can use AI. We spoke about object recognition, but also, of course, we've got speech recognition. If any of you use Android, you know how good that is, even in noisy environments. Natural language processing, things like sentiment analysis, which we'll go into later in the presentation. There's creative potential, such as style transfer, which once again we'll talk about later. Predictive capabilities, so if there's a house in San Francisco that's 1,000 square foot, what do we predict its price to be, for example? We can do that with enough data at our fingertips. Translation between languages, so things like Google Translate is now possible. And of course, my personal favorite is restoration and transformation. Now, the best way to explain what this is to see an example. And in the top right-hand side of the presentation, you can see this animation of faces. This is from the latest NVIDIA research. And the key thing to note here is that all of these faces are fake. None of these faces actually exist in the real world. They've been dreamt up, just like you'd have a dream about a face or a purple cat. You can dream up a purple cat in your head, even though you've never seen one, right? So the same kind of approach is happening here, but using neural nets to generate these faces from scratch. I think it was trained on celebrities, so they kind of look celebrity-like, because that's all of its knowledge of the world. So it only knows how to generate celebrity-like faces. So that's pretty cool. And if you'd like to see more experiments like this, you can check out AI experiments. Just Google that, and you'll get to aiexperiments.withgoogle.com. I believe is the URL, and it will allow you to essentially view all those in your web browser. So on to machine learning then. Machine learning is basically an approach to achieve AI that we just spoke about on the previous slide. Okay, essentially, these are the systems that can learn to find patterns in the data you present to it. Okay, now the key thing that's very important here is that these systems can be reused. So if I train a system that can recognize cats, for example, the same system can be used to recognize dogs just by changing the training data. Okay, without changing any of the actual code that was written to do that. And that's very, very powerful. So if we go back to the old days, you can see here how we might have made a spam filter. On the left, we would have had to write lots of conditional statements. If the email contains a word like Viagra, then it's spam. If it contains another word, it's spam, and so on and so forth. Now, this is not very scalable because there's kind of a constant battle between programmer and spammer, and they're trying to outwit each other all the time, and this becomes unmaintainable. So you fast forward to today, and you can see now we use machine learning to do this. So instead of explicitly defining the rules, we simply mark an email as spam, and then the machine learning will take all those tens of thousands of millions of examples of spam and figure out mathematically what words contribute to spam itself, and then mark it as so. So that saves us a lot of time and effort and allows us to do more important things. Okay, so what about deep learning then? Essentially, deep learning is a technique for implementing machine learning that we just spoke about on the previous slide. So this is more like one of the algorithms you can use if you wish. Now, one of these algorithms is known as deep neural networks, which you may or may not have heard of. If not, you will do by the end of this presentation. And essentially, DNNs are very loosely arranged to mimic how we believe the human brain to work. Essentially, it's learning patterns of patterns, okay? And we'll get into that in more detail in just a bit. Okay, so in summary here, essentially you can see how these three concepts are actually interlinked. The deep learning is the algorithm that drives the machine learning, which is the general implementation. And then the machine learning gives you this grand illusion of artificial intelligence, which you're all aiming for. Now, these concepts actually go back many, many years to the 1950s and 60s, but it's only now that we've got the power and the resources at a cheap enough cost to put some of these ideas into action. So, you know, the cost of memory has come down, processing power, GPUs, all this kind of stuff. Okay. So how do we train machine learning systems? Now, for this hypothetical example, I'm going to pretend that all of us are farmers. Okay, I know you're all from very different backgrounds, but we're going to pretend to be farmers, for example. But you can apply the same techniques to your own domains. So first thing, if we want to recognize apples and oranges, for example, we need to figure out what features or attributes we can actually record about these apples and oranges. So we might choose weight and color, for example. Okay, these are easy to recognize and measure in the real world. Now, if we go back to our high school maths for a second and plot weight versus color for some example apples and oranges, you can see on the screen here that the green apples have essentially clustered together in the green spectrum on the x-axis and are of a certain weight on the y-axis. And the red apples are also clustered together and are of a similar kind of weight. Now, the oranges, because they're more juicy, are a little heavier, so they're higher up and in the orange spectrum. So you can see here that if we can draw a line to divide our apples and oranges up, you can see with this yellow line here, we can say with some level of confidence that for any new apple or orange we measure, if it falls above that line when we plot it, we can say it's probably going to be an orange. And if it's falling below that line, it's probably going to be an apple with some level of confidence. So you can actually treat this as a very simple, naive machine learning system if we could generate that line using a computer program rather than just drawing it ourselves. And essentially, on a very simple scale, this is what the machine learning systems are trying to do behind the scenes using mathematics to separate the data up so you can classify it with the best precision later on. Now, a note on features and attributes. If we chose bad features and attributes, essentially like ripeness and number of seeds, you might get a scatter plot like this. And there's no meaningful way to separate that data up with a straight line in this case. Now, you might say, Jason, why would you actually choose such bad features here? And in the case of apples and oranges, it might be obvious to you that this is not a good set of features to use. But if you go back to something more complex, like brain tumors, image data, what features would you use in this case? It gets much more abstract when you're trying to deal with other types of data. And feature engineering, as it's known, to choose the right features to use in your system to get the maximum gain is, it takes time and practice to learn how to do that. And that's what a lot of the engineers around the world are paid a lot of money to do correctly. So more on that in just a second. Now, non-trivial data. In our example, we had just 2 features or attributes. What if we had 3? Well, in that case, you can see we would have to plot it on a 3D graph instead of a 2D one. So you can see this plane or rectangle, if you will, in 3D space. And instead of using a line, we're using this plane or rectangle. So anything above this rectangle is a cat in this example, and anything below this rectangle is a dog. Now, it turns out that machine learning systems actually use much higher dimensionality than 3. There might be 20, 100, thousands, maybe even millions of dimensions in the cases of images. And don't try and visualize what that looks like. I tried and I failed miserably. Our human brains can't comprehend that. But the mathematics is actually exactly the same. Now, instead of using a plane, you're using something called a hyperplane, which is simply 1 dimension less than the number of dimensions that you actually have, okay? But the mathematics is the same. You're just trying to separate the data out, but just in high dimensionality. So it should be easy then, right? We've got dogs, we've got mops. What could possibly go wrong? Well, it turns out that some dogs look like mops and vice versa. And my key point for bringing this up is that one of the biggest challenges is finding enough unbiased training data for the objects you're trying to recognize in the real world, in typical conditions you're going to see them in. If you're trying to recognize cats, for example, you're going to maybe need like 10,000 images of cats in different conditions. So maybe different stages of a life cycle, kitten versus adult cats, different breeds, at different sizes, different rotations, different angles, different lighting conditions, in a house, in a field, all these different examples. So you then have the best chance of the ML system learning what the cat pixels are versus the rest of the world, essentially. So it can classify it as best as possible. Now, the other point I want to raise here is that data is not always images. It could be data from text, sensor recordings, sound samples, and much, much more. I use images in the slides because it's more visual, of course, but it could be anything. So another thing I want to point out is a machine learning system cannot predict stuff it does not know about. So in this very trivial example here, we've got 2 pieces of training data, a dog and a chicken. And you can see the dog has 4 legs, is black, and is 10 kilograms. And the chicken has 2 legs, is orange, and 5 kilograms. Now, if we were to present this system with a cow, which it wasn't trained on, but we as humans know is a cow, so 4 legs, black, and 200 kilograms, this system would predict dog. It would think it's just a very, very large dog. And this is because it only knows about dogs and chickens when it was trained. And that would be the closest match. It's got 4 legs, it's also black, and it's just a very, very heavy dog, essentially, as far as it's concerned. So ML cannot predict stuff it does not know about. So what are neural networks then? These are all the rage these days, and anything that's doing anything cool seems to have a neural network involved in it at the moment. So we're going to go through this. Now, to understand neural nets, we're going to go back to our own human brains for a second. Now, our human brains consist of around 86 billion or so interconnected biological neurons, okay? And there's certain neurons in that clustering that recognize certain things. So there's a cluster of neurons that get excited, if you will, when they see the color black. There's a cluster of neurons in your brain that get excited when they see an eye or an ear or a mouth or a nose. Now, if all of those clusters get excited at the same time, they will link to other parts of the neurons in your brain to indicate you've seen a face, or your friend, for example, your friend walking down the road. And that's how you recognize a face. At least that's how we believe the brain to work. Now then, in machine learning, artificial neural networks are very loosely modeled in how we believe the brain to work. And instead of using this biology, we're using mathematics and statistics to essentially replicate getting excited about certain features in the imagery or data we present to it, okay? Now, the next slide is going to look very scary, but as long as you can add and multiply, we will get through it. So don't freak out when I change the slides. So this is an artificial neuron, also known as a perceptron, okay? And the best way to go through this is just to walk through the example here. So on the left-hand side, hopefully you can see my mouse, are the inputs, these white circles. Now, it's important to note that these inputs are numerical because computers only really know how to deal with numbers. So we're working very low level, and we can only use numerical inputs to the system. So these could represent, for example, pixels in an image. So if you had a grayscale image, 0 could represent black, 255 could represent white, and all the numbers in between could represent some shade of gray, okay? And each one of these white circles could represent 1 pixel in that big image, okay? Now then, what we do is we take the input and we multiply it by a weight. Now, these weights are just randomized to begin with, so don't worry where they come from, but just random numbers to start, okay? So you can see here, I've got 3 multiplied by a 2, which would be 6. 1 multiplied by 1 would be 1. 7 by 3 is 21, and so on and so forth. And you do this for all the inputs and then simply sum them together. So you'd get a total by multiplying the inputs by the weights and adding them together. You then add this thing called a bias, as you can see in the orange circle at the bottom there, to that total to give you a grand total that's in that yellow circle. In this case, it's 42 if you work through this example. So does everyone understand the mathematics of that? Please say yes or no in the chat. Don't worry about understanding how it learns. Just if you understand what's going on with the math, just the adding and multiplying. Okay, good stuff. Okay, so that's the first half of a neuron. The second half of a neuron is something called the activation function. Now, this is just a mathematical function or a graph, if you will, which has an x-axis and a y-axis, whichever way you prefer to think about it. And it's going to take that grand total we came up with, that 42, for example, and transform it into another number using whatever graph you've defined to use. And that's going to come out at the end here as the output of our neuron. And that output of our neuron then simply becomes the input to other neurons in the system, okay? So everyone, once again, are you with me in terms of what happened just there in the whole of this neuron? So just understanding the mathematical flow. Okay, resounding yes. Don't worry if you say no, I'm happy to explain anything. Okay, everyone's yes. Okay, good stuff. So the next slide is going to look even scarier. Oh, someone said no. Are you trolling me or is this actually no? If you have a question, please ask the question. What is it you don't understand if you are not understanding the flow here? The last part, sure, okay. So the last part is this thing called an activation function. This is essentially just like a mathematical graph. So given some x value, if you looked up the value on the graph, it's going to produce a different y value, okay? Now, what graph you choose is down to the programmer in the system, so don't worry about that, but just know that it's just going to take our grand total and transform it in some way to give us another number that's finally output from the system, okay? Does that make sense? We'll get into how the weights are done later on, so don't worry about that. We'll talk about it on the next slide. Okay, cool. So next slide. So now what we're doing is we're simply taking that example neuron we just saw and applying it in a much grander scale. So all of these yellow circles are neurons, and all of these blue circles at the end are neurons, just like we saw on the previous page, okay? They're doing exactly the same mathematics. So let's walk through this. Now, in this real example, we've got an actual grayscale image, which is 28 by 28 pixels. If you were to unravel this into one big long line of pixels, you'd have 784 pixels. So we're going to use these 784 pixels as our input to the system. And remember, those pixels are just numbers, right? They're just numbers between 0 and 255. So instead of having 7 inputs like we did on the previous slide, we've now got 784 inputs, okay? Now, each one of the neurons in this first layer is simply sampling every single one of those inputs and doing the same maths as we did on the previous slide. So as we can see, it's taking the inputs, it's multiplying it by a weight, which is random to begin with. It's adding them all together, it's adding a random bias, and it gets a grand total. It passes it through the activation function, and then spits out an answer, okay? And each one of these yellow circles on this slide in the first layer is doing that. Everyone with me for this first layer, just say yes in the chat if you're good on that. Okay, cool. Now the second layer here, which has also got these yellow circles, instead of sampling the original inputs for 784, it's actually sampling the outputs of the first layer, okay? So whatever comes out of these neurons after all those transformations have occurred is what the second layer actually samples. And then the same thing happens again on the third layer, which is known as the output layer in this case, which samples the outputs of the second layer, okay? Now, can anyone guess why there are 10 neurons in the output layer? Feel free to write it in the chat if you can have a guess at that. Yes, correct. There are 10 numbers we're trying to predict here. We've got the numbers 0 to 9. So essentially, that's why there's 10 possible neurons to use in the output layer. And the way we basically predict what we think we've seen on the input image is we simply take whichever output neuron has the highest number coming out of it is the system's prediction for what it thinks it's seen for the input image in this case. Now, as I said, all those weights and things were random to begin with. So essentially what's going to happen here is that we present it with the number 9 and it will go, hey, I think it's a number 2. And that's clearly incorrect. So what we then do is we need to train the system. So what we will do here is we'll go back through all the weights that contributed to number 2 being the highest number, and we'll penalize them, we'll make them slightly less, okay? Such that after we train thousands of times on different number 9s and different numbers 0 to 9, eventually the weights will adjust themselves such that in most cases, when we present a number 9, it will pop out the highest number to be in the number 9 spot on the output layer. Everyone with me on that? Does that kind of make sense? Okay, cool. Now I saw a question about the number of neurons in the layers and that kind of stuff, and why 2 layers. So essentially, for this example, 7 and 5 works well with this kind of data set. This is the MNIST data set for handwritten digits. These numbers, basically, it's your job to figure out what works best. The more neurons you have and the more layers you have leads to higher chance of overfitting your data. What that means is that it's going to get very good at accurately describing your example data, but won't be able to generalize when you encounter new digits that it's not seen before. So you want to have the minimum number of neurons and layers that give you decent results in your accuracy in order to allow the system to be more general for things which you have not yet seen in the real world, for example. More about the bias. So you can think of the bias as an optional offset the system can use at the neuron layer in addition to the weights and multiplications, just to kind of offset it. If you think of like a line graph, y equals mx plus c, you can think of the bias as a c in that situation. So if you're trying to draw things and separate things with lines, you can think of it as a c offset the bias, essentially, okay? All right. Why is there no neuron to indicate ambiguous and another one to indicate not a digit? So the system, as you just saw, is just mathematical operations. It has no concept of digits and rest of world data, okay? it will always predict a number. Okay, it's been told about the world that it's always going to be a number from 0 to 9 presented to it. So whatever you present to it, even if it's not a number, it's going to try and see what is the closest match and predict a number in this case. If you wanted to cater for things that are not numbers, you might have to give training data for not a number, for example, and have like lots of squiggles and other letters and things, and have 11 neurons in the output. And one of those would be maybe to represent all the things that are not numerical looking, for example. Okay. Okay, awesome. So let's talk about the types of output. Oh, sorry, one more question on the inputs there. How do you define the number of inputs? For example, the 784 inputs. So in this case, we're using an image, okay? This image was 28 by 28 pixels. If you multiply 28 by 28, it's about 784. That's just the number of pixels in that image in this case. If it was things other than image data, then it'd be your features or attributes, however many features or attributes you had that you were measuring, essentially. That's what the inputs are. Okay, cool. So over to types of outputs. Now, in my role, I typically deal with regression, classification, clustering, and sequence prediction, these main four. So regression is simply predicting numerical values. For example, what do we think the price of a house is given its square footage, okay? Classification might be for images, like what can we see in that image? Is there a dog? Is there a cat? Is there a human? Then we've got clustering. So for example, on Amazon, maybe you're buying a toothbrush and you want to recommend toothpaste because that's a similar thing. We can cluster like objects together. And then we've got sequence prediction, what comes next in a numerical sequence like 2, 4, 6, 8, or even using words. If you want something done blank, do it yourself with enough text and understanding of human language, we can actually fill in that blank, which is probably properly in this case. So how do we use the output? Well, in this example of a pet feeder, essentially machine learning is actually a very small part of the overall system. So you've got a very small part of the system looking through a camera to give predictions on what it sees in the world outside. And if it's 80% sure it sees a cat, we might then open the pet tray to feed the cat. If we're only 75% sure, then maybe we as a programmer will decide it's not good enough and we won't open a tray. So my key point here is that ML is a small part of the system and the programmer actually still then makes decisions what to do with that knowledge of the world around it. And of course, you've then got to make the hardware, you've got to make the apps and all the regular stuff that is just regular software engineering, okay? So you've got a lot of other stuff working with the machine learning. So how is Google using machine learning? I get asked this a lot. You can see here that the growth of the ML repositories at Google has grown exponentially. And this is a little old now, but you can imagine it's still growing very fast. And some of you may have heard of these products. So Google Photos, for those of you who haven't, essentially on Android and now iOS as well, you can install Google Photos. And if I search for dog in Google Photos, it'll bring back every photo I've ever taken of a dog, even though I didn't tag it as such, okay? And that's very powerful. So next time you're at the pub or your bar with a friend and you just got back from holiday, you can just search for beach to get all your beach photos instead of scrolling through your photos for half an hour trying to find your beach photos. It's very, very powerful and very, very cool. Gmail and Inbox has smart replies. So if you're on the go, you can simply tap on a quick response. It will analyze the email that was sent and kind of give common answers it expects people to say. That's very useful if you're walking or using your phone when you shouldn't be. That can just help you out reply to things faster until you're more available. And then the final shout out here is around robotics. At Google, we've got this thing called the arm farm. And essentially, it's trying to learn how to pick up objects. Now, as humans, we don't think about how hard it is to pick up an object, but it's actually very, very hard to do so. Objects have different weights, different textures, different shininess, different forms. And there's so much that can go wrong when you pick up an object. Now, what you see here is a whole farm of arms doing this. And when one arm learns how to do something, all of them do because they're connected by the cloud, which is pretty awesome. And it turns out that you can even simulate this using virtual reality and a physics engine, for example, and let the arm farms go to work in the virtual world until they get pretty good. And then you can then hook it up in the real world and it'll be most of the way there by the time it has to start using real world objects, which is quite nice too. So consider how you might use simulations to actually train your data, train your systems too. And then there's a whole bunch of other Google products and services. You saw in the charts over 4,000. I'm not going to go through all of those, but you can go through these in your own time. These slides are online if you just search Jason May's ML 101. Okay. Anyone heard of Autodraw? Yes or no's in the chat? Okay, a few of you have seen it before, and maybe some of you haven't. Okay, so on the left-hand side here, you can see that this is my attempt at drawing a cat with my touchpad, and it's very, very bad. Now, what's happened here is Google has recognized that I've tried to draw a cat and then replaced it with the perfect clipboard. Clip art, sorry. So now even someone like me who is not amazingly creative at drawing can actually produce fine pieces of art. Now, how does this work? Well, essentially, we got hundreds of thousands of people to draw common objects like chairs, tables, cats, dogs in the web browser. And we use that data to then train our system to recognize the strokes and the way things are put together. Now, it's important to have unbiased data here because it turns out if you ask someone from, say, China to draw a chair, they might draw the chair with the back on, say, the right-hand side and then the seat coming out towards the left. Whereas if you ask someone to draw a chair in America, they might have the chair with the back on the left-hand side and the seat coming out to the right. And if you don't have that training data in your samples that you're training on, your system's going to be biased and it won't recognize the instance which it didn't have in the training data. So to make sure your systems work well for everyone, you're going to be very careful not to have a biased training data. Next up, Soli. Who's heard of Soli? Quick yes or no's in the chats. Oh, everyone's going no for this one. Okay, well, you should do. This is a really cool piece of technology. This is from Google. This is essentially radar on chip. Now, what you can do here is put this into something like a smartwatch, and then it will send out radio waves to the world around it, and then analyze how they bounce back using machine learning, and we can figure out what's happened. So you may have used a fine gesture in that moment. We can detect that gesture, and it allows you to control things like the smartwatch screen, which might be too fiddly to use otherwise. So, looking towards the future, maybe we have a world where there is no screen, things like a washing machine or your refrigerator, which you can then control just by a flick of your wrist, for example, which would be quite cool. So yeah, very cool piece of hardware. And if you want to know more, just feel free to Google Project Soli. Anyone heard of Pixel Buds? Quick yes or no's in the chat if you have or haven't heard of Pixel Buds. Mixed bag results. Okay, so Pixel Buds were released with the Google Pixel phone when it was launched a couple of years ago. And essentially, this is Assistant built into the earphones. So if someone is talking to me in Chinese, I can hear them in English in my ears, which is very, very cool. Now, let's just take a moment to appreciate how cool that is, because I grew up with things like Star Trek when I was a young boy, and there was that thing called the Universal Translator. And this was the stuff of sci-fi not too long ago, but now it's actually here and works pretty well. So we've come a long way. It's a really exciting time to be developing for things right now. Okay, next up, Google Lens. Who's heard of Google Lens? Anyone heard of this? Shout out in the chat. A few no's. Well, okay, mostly no's. Okay, so this was launched with the latest generation of Android smartphones for Pixel line from Google. And essentially, it's built into the camera app, the default one. So you hold up your camera to the on your smartphone to the world around you, and you can get contextual information in real time. So you can see here, you put it towards a shop front, and we can recognize what store it is and give you the details, the reviews, the ability to book a restaurant or whatever it might be that you need to do in that moment, or just by holding your phone up to the world around you. Or maybe you see a flower that you want to buy for your girlfriend or something, and you don't know what flower it is. You can simply hold your phone over it and find out what it is, and then go to your florist and order some. So yeah, this is getting better and better with time. And if you know anyone with a Pixel phone, 1, 2, or 3, I believe it's supported on, go check it out because it's a really cool technology. So how are others using machine learning? So these examples are more kind of cutting edge. They might not be scalable right now, but it's a good kind of introduction to where things are going potentially. And these are both from my team and also beyond my team externally to Google as well. So first up is robotics. There's a really cool company called Boston Dynamics who made this robot doing a backflip. Now, I can't do a backflip. This robot is better than I am. And if you asked me 10 years ago, would I expect robots to have this much kind of dexterity right now? I'd be like, oh, no way. You've got many, many years to go before it's this good. But lo and behold, it is doing backflips before our eyes. Now, there is some online debate whether or not Boston Dynamics is using specifically machine learning to do this, but that's besides the point. I've seen robots that have learned to walk using machine learning, such that if you kind of remove a leg, if it's damaged or something, it can adapt in real time to learn how to walk again and survive with only 3 legs instead of 4 or whatever it might be. So machine learning can be used to do these kinds of things, even if Boston Dynamics did not. But yeah, very cool company nonetheless. Style transfer. Here you've got a regular image on the left-hand side. In the middle, you've got an image from your favorite artist, in this case, Van Gogh. And then the machine learning will create an image of your photo in the style of the artist you presented to it. Now, the key thing to note here is that this is not just a fancy Photoshop filter. This is machine learning. And that's important because 1, it's very fast because it's just a bunch of mathematical operations going through the system. And 2, it means you can actually tweak those mathematical operations to get variations on the styles and effects. So it allows you to generate new ones as well, which is pretty darn cool. So essentially what's going on here is it's learning the what objects appear in the first image and the essence of the style of the second, okay? And then it combines those to produce the output. Next up is video generation. What happens if you try and create videos of common scenes based on the knowledge of the training data? So you can see here, we've got beach, golf, train stations, and babies. And if you have a quick glance, it's kind of believable. You look at the babies in more detail, you realize the faces are a little bit messed up. But remember at the beginning of this presentation, you saw some very good faces from NVIDIA. So if this piece of research, which is a few years old now, was recreated with NVIDIA's research, the results might be much better, in fact. But this leads to the question, if we can generate videos that don't actually exist, remember, these are all dreamt up, maybe in the future we'll have the ability to, as a Hollywood producer, go, hey, I need a clip of a guy getting onto a train, and the machine learning system can just generate that clip in nice high quality for us. And there's no copyright issues or royalties because it's literally been invented right there and then. So very exciting times ahead if this technology progresses to a more usable level. Next up, skip thought vectors. What happens when you combine 2 machine learning systems? One has been trained on romantic novels, and the other one has been trained on how to describe photos. You might end up something like this. He was a shirtless man in the back of his mind, and I let out a curse as he leaned over to kiss me on the shoulder. Now, clearly, they're in a fight here. That's not what is going on. But if you can only describe the way in a romantic way, that's maybe what you would say. So the point here is that you can actually use machine learning to do quite creative things as well. You can imagine attaching this kind of system to a car and just driving it around the world and seeing what the car sees in a poetic way or something like this. It could be quite fun. Understanding images. So obviously cameras are an entry point to the world around us. Someone made this thing called a thing translator. So essentially it recognizes the object in the photo you take a photo of, and then it converts that using Google Translate or some similar technology into a different language and shows you how to say that thing in the language of your choice. Now, just like 10 years ago, you probably would need a small startup and a lot of investment to make something like this and a few years of dev time. Using the APIs and examples I'll show you later on in this presentation, you can make this, if you know some basic JavaScript, in just a couple of hours. This is very easy to now achieve, okay? Treasure hunt, yeah, if you can recognize objects, obviously you can do like gamification of things. You can go on a treasure hunt, that kind of stuff, find things in the real world. And then here we've got dragon spotting. This is one by my team that I personally was involved in. There was a movie called Pete's Dragon by Disney that came out a few years ago. It's aimed at children. And the key part of this movie is that only the children could see the dragon, okay? So we're like, how can we bring this to life to make people go and see the movie? So what we made was a combination of augmented reality and machine learning. So you have to go and find objects in your house, like a sofa, a lampshade, a TV, things we knew most people would have. And once you pointed your phone at that object, we could augment Elliot the Dragon into the scene. So you could take a photo and prove to your parents that the dragon was real and you saw it in your house. This is quite a creative piece, and we use the Cloud Vision API to recognize the objects. And there's a great success for both the Cloud Vision team and, of course, Disney. predicting complexity, identifying patterns and behaviors at scale. So essentially, anyone heard of AlphaGo? Maybe some of you play Go. What happened here is that Go is a very complex game, computationally speaking, because the number of permutations that can exist are crazy high. Like there's like less grains of sand on Earth or something than there are combinations of playing this game. So you can't just brute force this like you can for like chess and other games. This needs some level of intelligence to beat a human expert at this. And lo and behold, AlphaGo, which is by DeepMind at Google, beat the world champions at Go not too long ago. If you're interested in how they managed to do that, using like reinforcement learning and all this kind of stuff, you can check out a Netflix documentary, I believe, which goes into way more details than I can in this presentation on what they did to achieve these great results. Optimizing user experiences, designing for context and personalization. Essentially, Spotify is a great example of this. If any of you use Spotify, you listen to a few songs and then it starts recommending new ones for you to try. And of course, it's using some form of machine learning behind the scenes to do that. Now, what it actually uses as its features and attributes is secret source to Spotify, but we can take a guess, of course, that it might be something along the lines of beat matching, listening to the lyrics and understanding the words used or the rhymes, that kind of stuff. Maybe the artists and all that kind of stuff to see the different genres and things. And all of those will be inputs to the system that they can train on to then predict what you're most likely to listen to next or want to hear next. Project Muze is another one by my team. This is where machine learning and fashion comes together. So if any of you are from a creative background, you probably are aware that sometimes when you're designing something, whether it be fashion or even just web design, you have creator block. You kind of get so far and then you're like, oh, I don't know what to do next. And you go away and have a cup of coffee and then you come back to the problem. Now what happens if the machine learning can suggest alterations in that moment when you have the creative block and suggest what to do next based on its knowledge of style or fashion or design? And this is what this project tried to do. So it helps the person design that dress by giving suggestions along the way. So this is a great example of human and machine coming together, which I think is a very strong point right now, where individually they might be so-so, but together they can actually do great, great things. Conversing with users, natural interactions in our everyday lives. This is another one by my team called Disney Book Ears. Essentially, if any of you have children, I'm sure you're familiar with story time, and you'll read a book maybe before you go to bed with your child. Well, what if your Android smartphone could actually hear you, and then when you say things like, and then the lion roared, it could be connected to your speakers in the house and actually make the sound of a lion roaring, okay? Well, with Book Ears, we can do that. And imagine if you had a very smart home with smart lighting, if you were in a thunderstorm or something in the book, we could even make the lights flash and all that kind of stuff too. So yeah, really magical experiences, and it was a very nice creative piece using cool technologies. If anyone here is a fan of Westworld, let me know. Also, if you don't like spoilers, then mute for the next slide, because I'm going to tell you something about Westworld, the TV series. Essentially, in Westworld, there's a character called Aiden, and it turns out that Aiden is actually an AI entity in the TV series. He's actually like a robot. And we thought it'd be really cool to actually bring Aiden to life for real using machine learning. So you could talk to him online and ask him questions about the upcoming TV series. So what we did is we used natural language processing to understand users' queries and then allow Aiden to respond in the most appropriate way. This led to over 400,000 unique conversations, I believe, and even went on to win an Emmy Award, as it was one of the first times like Hollywood had basically brought together a kind of character in this way. So we've seen some really cool examples, but like, how can we go and make these? What products and services can we use to bring these to life? Obviously, I work at Google and I use these day to day, so I'm going to be talking about Google products, but of course, feel free to use others if you're more comfortable with those. But there are some benefits to using some of our systems, which I'll go into in just a second. So depending on your level of experience, you can see on the right-hand side here, got the pre-trained models. If you're a beginner to machine learning, or maybe not an expert programmer even, these pre-trained models that are web-based are very easy to use. Now, if you have something that the pre-trained models can't detect, maybe you're working on a new launch of a vehicle, a new car, for example, that doesn't even exist yet, and you're trying to recognize it, then you're going to want to use our retrainable models. These are still pretty easy to use. They work in the web browser, but you've got to give us training data to train on. And then on the far left here, we've got the custom models like TensorFlow, which are for the kind of machine learning geeks amongst you and the hardcore programmers. This is very, very low level building blocks, but allow you to do pretty much anything. So let's go through all of those right now. So first up, we've got the Cloud Vision API. Now, as you expect, you send us an image via the web, and we'll send you a JSON object back containing what we think we can see in that image. What can it recognize? Quite a few things. So first off, we can give you all the labels of the objects we see in that image. So, cats, dogs, all that kind of stuff. There's thousands of labels we can detect. So there's a good chance we can recognize most common objects. We can also detect faces. So we'll tell you where in the image the face is. We'll give you the bounding box for that. And even better, we can tell you what kind of emotion we think the person has. Are they happy? Are they sad? Are they angry? We've got OCR, optical character recognition. So if there's any text in that image, we can extract the text and pass that back to you to then do something useful with. We've got explicit content detection. I don't think I need to say any more of that. It's pretty obvious what that does. But this can help you filter explicit content from your sites, maybe, if you want to kind of use our service to do that. And then we've got the landmark detection. So if there's any famous landmarks, like the Eiffel Tower, we can give you back like the knowledge graph entry that we know of the object. So, it's located in Paris and all this kind of stuff. So you can give you extra information about famous objects. And the same for logos as well. If we see logos, we can, of course, bring back data about that brand. Next up, we've got the natural language API. In this case, you send us text and you get a bunch of things back. First up, we can do entity recognition. So using Google's knowledge graph, if we can see something that is important in that text, like people's names, organizations, locations, events, products, all that kind of stuff, we can tell you what we found in that text. So then you don't have to worry about those kind of filler words like and, buts, are, and eyes, and all that kind of stuff, and just concentrate on the interesting words to then do something useful within your system. Very, very powerful. We can also do sentiment analysis. So is a statement positive or negative, or is it neutral? This might be useful, for example, if you had like a commenting system on your website and you wanted to kind of remove abusive comments or negative comments. This might help you to do that. Now, all of these things are supported in multiple languages, which is growing over time. So check out the website for more details, which I'll show you in just a second. And if there's any grammar geeks amongst you, we also do syntax analysis. So we can break down the sentence into the nouns, pronouns, verbs, all that kind of stuff too, which might allow you to do something useful in your system as well. Next up is the speech API. Essentially, you pass us audio, and in real time, we'll send back predictions of what we can hear in that audio. Okay, and this is supported in over 80 languages, which is pretty impressive. And the results occur in real time, or close to real time. It'd be like maybe 100 milliseconds delay or something like this. Basically, the latency from the server to your computer. And what's really cool here is that our systems are trained to work even in fairly noisy conditions, because we've trained our machine learning in noisy conditions as well. So when you're in a bar and you're talking to our voice recognition system here, it will still have a good chance of recognizing what you say. Now, if you are making a system that's very specific, so maybe you're trying to make a video player, which is voice activated, for example, play, pause, rewind, fast forward, saying keywords like this, you can pass us these things called word hints. And what these are the words you expect to hear to use your system. So we can be slightly biased towards those words. So when you're in like really, really noisy conditions, maybe we can be slightly biased towards those words. And if it sounds fairly similar, then we can just kind of say, hey, I think you said play or pause or whatever it might be. So yeah, very cool technology there. Next up, translation API. Here you send us text in one language and we'll give it back to you in another language. So give it in English, get it out in Spanish. It's basically Google Translate as an API, essentially. So yeah, I won't go into that anymore. That's pretty simple. Finally, here with the video intelligence API, this is similar to the image one, except for videos. So imagine you took a video when you went to the zoo, and you want to basically make a panda compilation at the end. Instead of going through the whole video yourself, you can just pass it through here, see where the pandas occur, and automatically crop it to those moments, and end up with a panda compilation from that video, for example. So very useful for understanding what is in the frames of videos. And all of these that I just spoke about, you can try online without even touching one single line of code. So if you go to these URLs, and once again, the slides are available. If you just Google Jason May's Machine Learning 101, you will find these slides with these links, and just click these, open them in your Chrome browser or whatever browser you like, and go and paste in an image, paste in some text, talk into your microphone, and see the results that you get back and see if it works for your use case. You may find most of the time these are good enough. It's very rare you actually have to train your own system from scratch, in fact, and we'll get into that in the next few sections. So yes, training your own system. TensorFlow is essentially a machine learning library that was open source a few years ago, which was originally made by Google. And you can think of this as a toolkit, if you will. It's got all the basic building blocks you could possibly need to do all that crazy maths we spoke about earlier in a nice, easy to use way. Now, I say easy to use, that is assuming you know some background on machine learning. It's very technical. But basically, if you go through the tutorials online, you can get started much faster with that. Now, there's some benefits of using TensorFlow over maybe other libraries if you're planning to use the Google Cloud infrastructure. So first of all, there's these things called TPUs, Tensor Processing Units, that are only available on Google Cloud. These are custom hardware developed by Google that are essentially faster than graphics processor units, GPUs, in some cases. So typically, you'll train an ML system using your graphics card because it allows you to do many parallel operations at the same time. But TPUs can do what might take a GPU 4 days to do, it might be able to do in 4 hours, okay? So if you've got really large data sets that are very, very intense in the kind of processing, then TPUs may be good for you, and they're only available on the Google Cloud. We've also got Cloud ML Engine. So if you've written your code in TensorFlow and you've made a model that was made from TensorFlow, you can then deploy that model to Cloud ML Engine. What that means is that it's going to scale automatically from 1 user to 10,000. And you don't have to worry about having all the servers scaling and dealing with the infrastructure. It will just scale automatically and just give you a web endpoint you can call to predict whatever you are trying to predict. So it basically creates an API for you, super simple. So yes, these are all available right now, and you can find TensorFlow on tensorflow.org and GitHub if you just Google TensorFlow. You can download it and get started right away. Next up is Dialog Flow. You saw that Westworld example where we created a bot. This is basically how we did that, essentially. You can make a conversational assistant on Dialog Flow in about 10 minutes. It's a super easy to use web interface. But for the programmers among you, there's also an API, of course, as well. And that allows you to do more advanced things like integrate with your backend systems and do custom things that you want to process and all that kind of stuff. So imagine you wanted to make a weather bot, for example. You might have to just train it by giving some examples of phrases someone might say. So you might give it, hey, how's the weather? Or what's the weather today? Now, what will happen behind the scenes is it will use natural language processing to then analyze those examples you gave it. So when someone comes and says, yo, what's up? I want to know what the weather is, which wasn't in your training examples, it will know it's the same question and route it to the right part of your program automatically. So that's very, very powerful and saves you a lot of time writing your conditional if statements to try and handle every single phrase someone might say, which is infinite, basically. People can say the most random things at times. So what's cool about this as well is that once you've got your bot created on there, you can then deploy to things like Facebook Messenger, Google Home, Alexa, all those ecosystems in one click of a button as well, which is very, very nice. So you've got integration of all those things too. This is available on web or mobile and is super simple to use. So go and just try it out. It's really fun to hack with. So closing thoughts here. As you can see, machine learning and data science is a mixture of many different disciplines. My personal background is this blue circle, the computer sciencey circle, and the cloud computing circle. But there's many other areas that I still need to learn a lot in as well. And it takes time and money to basically learn all that stuff and make systems that utilize all these things. But if you can, you may just have the edge versus your competitors who are not using machine learning. And with time, as I said at the beginning of this talk, every vertical will be influenced by it in some shape or form. So it's good to start experimenting now to see what returns you can get. And yeah, of course, it's already influencing our everyday lives, products, and of course, services right now. So that's all from me. If you enjoyed the deck, you can connect with me online. And if you have any questions that you haven't asked today, you can also ask those online too. LinkedIn is probably the best way to get hold of me. Please write a message that you met me in this presentation. Otherwise, I might ignore you. So yeah, connect me on there. And thank you very much for listening. If you've got any questions, feel free to write them in the chat and I can try and answer them now as well.
Okay, thank you, Jason, to deliver the great talk. And then if you guys have any questions, just feel free to leave in the chat window. We will try to answer them, but we are running out of time. So just like a few quick questions.
Sure. Yeah.
One person asked your thoughts on Keras.
Yeah, someone asked about Keras. You know, it's a personal preference what you want to use. If you're familiar with Keras and all that kind of stuff, then feel free to use it. I just mentioned TensorFlow for the benefits you get by launching the models in the Google Cloud and that kind of stuff. That can give you an edge in training time, maybe. But use whatever you're familiar with. It doesn't really matter too much, to be honest. So, yeah. Question: given the example of artwork style transfer to create some new artwork, how good is AI with respect to authenticating artist work? E.g., is this a real piece fake? Okay, so yes, you may have heard of deep fakes, which is essentially the ability to generate imagery using GANs. Now, there is some research into this around detecting what has been generated by a computer. So there's actually neural nets out there that try and detect images that have been made by a computer, in fact. And this is an ongoing piece of research. Some people who release these generative models actually have techniques to detecting their own work, for example, but it's very much at the convenience of the person who wrote that system. But there's ongoing research into detecting this stuff, but it's a very open-ended question at the moment. But there are telltale signs. I think at the moment things aren't perfect, so you can tell some artifacts and things which you can use to detect it's probably faked. What else have we got here? Can the activation function change in different interactions, or is it fixed in the model? Once again, this is a parameter you can specify when you're designing the models and things, how that should work. Part of the fun of using things like TensorFlow is you can go that low level and define all of that kind of stuff. Like if you want to use like ReLU over other kind of activation functions, you can choose that when you're designing the system, or you can specify it as a hyperparameter at runtime sometimes too, if you've exposed that as a property. So it depends on who made the model and how they made it, essentially. What is the granularity of your sentiment analysis tool per paragraph, sentence, entity? Okay, I think it's, from the way, when I've used it, it's per the sentence you present to it. So if you give it one sentence, I believe it's going to analyze that as a whole. I can get back to you on that, but I believe it's as a whole for how I've used it so far. That seems to be how it works when I've tried it. After mass adoption of deep learning, what will be the future software developers do? Okay. As I said in the examples, there's still a role for software developers. Machine learning is often just one small part of the big overall system, like that pet feeder we saw. So I don't think software engineers are out of a job just yet. There's still many other parts of the system that need to be designed: the user interface, the hardware, the apps, and all that kind of stuff, right? So I think there's plenty of stuff for software developers still to do. What's your experience of model interpretability using? I'm not familiar with the tools you mentioned, Lime, Yellow Brick, and stuff. Maybe if you connect with me online on LinkedIn, we can talk about that in more detail. Can you use TensorFlow without the cloud? Yes, you can. TensorFlow is a machine learning library. It's open sourced on GitHub. You can download that. You can npm install or pip install TensorFlow, however you wish. And that just works on Ubuntu, essentially, or whatever Linux distro you've got. And you don't need to be in the cloud to use it. And you can actually export the models to work on mobile phones as well. But you have to be cautious of how much memory they use, of course, because mobile phones have limited memory, but it's all possible. Yes, we don't need the cloud to work. Are there feature engineers at Google? Yes, I'm sure there are plenty. There's many teams at Google that have machine learning in them and so are using machine learning, and I'm sure people in that team are very good at learning how to deal with the vast amounts of data that Google needs to use to make their systems, and choosing the right things is part of their daily job. Yeah. What's a good way to learn ML? So yeah, I mean, this was a good introduction, but of course it doesn't get into the programming. If you're interested in something to check out next, check out Google's MLCC, Machine Learning Crash Course. It goes into actually the Python code and stuff, so it's kind of getting your hands a little more dirty. And that's a good next step, I think, after taking this one. That will go through TensorFlow at least, if you want to learn TensorFlow. Okay, this is the last question. For the brain tumor analysis to work well, one would need millions, hundreds of thousands of medical images. Without that, stuff to train on. What's being done to reduce the number of criteria? Okay, so data is important. There's no way around that. You do need at least some decent amount of data to train. However, if you don't have enough data, there are two kind of things. You can either make the algorithm you're using not require as much data. That's very much down to your ability to innovate in that respect. But the other thing you could potentially do is generate new data. And it might not be applicable in all cases, but if you're trying to recognize faces, for example, from the example data you've got, you might be able to distort those, change the brightness, change the lighting, crop them in different ways, just to generate more variety of the data you already got to give you some more examples.